We have Brebner, he is an open source technology evangelist and Insta Cluster by Spot by Lab App. He will be talking about the spinning your drones with Cadence workflow, Apache, Kafka, and also TensorFlow. Thank you.
Hello, I'm Paul Brebner. I'm the open source technology evangelist at Instacluster. I'd just like to thank the API Days Hong Kong organizers for the invitation to present again at the conference this year. So this talk is an extension of the talk that I gave last year with some extra work that I've been doing and with the potential for more extensions even into future years as well. So it's spinning your drones with Cadence workflows, Apache Kafka, and TensorFlow. So I work for Instacluster. We provide a cloud platform for big open source technologies. And a recent addition to our platform is Uber's open source Cadence for workflow orchestration. So this talk is about Cadence, but it also includes Kafka and TensorFlow. So workflow orchestration is a simple concept. It's all about task ordering. A workflow starts at the beginning, forms the first task, forms another task in sequence, and ends. So that's simple, but in reality, things are a bit harder. And that's where Cadence comes in. Workflow orchestration with Cadence. This borrows from the bicycle pedaling metaphor. Pedaling with a high cadence or revolutions is called spinning. Mashing or grinding is slow and bad. So you want to be spinning your pedals fast. Cadence is horizontally scalable. So this is the first challenge in the real world. You don't want to limit the number of workflows that are executing concurrently. So with Cadence, the number of workflows is unlimited. Well, how does it do this? Well, it actually uses event sourcing to efficiently save the state changes as the workflows are executed. So rather than saving the whole state for each change, it actually only saves the state changes. Cadence is also fault tolerant. Workflows can and do fail, and then they recover using, again, the event sourcing model. So essentially, you just replay the state change history to recover the current state at the point of failure. In Cadence, workflows are just code. So this is another feature of Cadence, which is quite appealing to developers. You don't need to learn any special language or anything. You just write it in code. So here's a workflow implementation of two tasks executed sequentially, task 1 and task 2. Here's an overview of the Cadence architecture as we provide it as a managed service. At the back end, there's databases which actually do the persistence aspect. Cassandra or Postgres are possible. Kafka and OpenSearch are also included but optional. They're used for the advanced visibility mode. We provide the managed Cadence services. Then you as a customer will run your clients and workers. So you'll write the code and then run those, which communicate with the Cadence servers using APIs. Java and Go clients are currently supported. So Cadence activities, including things like backwards cycling, can fail. Activities are a core concept in Cadence. Remote calls can fail, so you wrap them in activities. They can contain any code. Activities are executed at most once and can be automatically retried on failure. So what are some good use cases for Cadence? Well, where you've got hundreds to potentially millions of running workflows, where you have long running processes, sleeping and schedule tasks, for stateful fault-tolerant applications, for complex workflows, integration with unreliable external systems, integration with streaming and event-based systems, for example, Kafka, and where you've got relatively short workflows. So hundreds of steps is good. Long workflows, maybe with thousands of steps, may take a lot longer to replay the history due to the event source mechanism. So some example domains include financial, retail, and one that I picked to build a demonstration application around is delivery. Spinning your drones, a drone delivery application. So in my drone delivery world, there are some workflow steps, naturally. Drones start out charged, ready to go at a base. They get an order to deliver. They fly to the order location, which is a shop, and they collect the order. They fly to the delivery location and drop the order to the customer. Then they fly back to the base, recharge, and repeat. So here's an example of drone delivery flight. This is just one leg where it flies. So this is all of the legs, base to order location to delivery location, back to the base location again. We imagine perhaps that this is some island where the pirates are wanting to receive an order via drone delivery before they go off hunting for the treasure. And here's an example of a single leg. This is the drone waypoint flight calculation. This is where all the work is really being done in the simulation as it computes the flight path of the drone. So this is the example of the returning back to base leg. The drone flight path is computed inside an activity. It uses location, distance, bearing, speed, and remaining charge, and it's computed every 10 seconds. And the advantage of doing this inside a Cadence activity is that on failure, the drone won't crash, but will continue flying from the last location. So, well, let's look at the overall architecture of the system using some swim lane diagrams. There's two workflows. The first workflow is specifically to do with the drone flying and location, and various steps to do with the drones themselves. So it includes things like starting, being ready, waiting for an order, movement activities, recharging, and then repeat. So we actually end up repeating a drone workflow. We don't start start a new one. We just essentially restart the same workflow each time. But it turns out that orders are also stateful as well. You want to know what state your orders are in. So we actually use a workflow for orders as well. So this includes things like starting, generating locations, being ready for the drone to pick up the order, updating locations, and successful delivery, hopefully at the end. So we've got two workflows, but they also need to interact with each other. So we need some coordination between the workflows. We use a mechanism provided by Cadence, which is asynchronous signaling, which enables signaling between workflows. But we also thought it was interesting to introduce Kafka into the mix as well. So Cadence meets Kafka. So in step one, as we just go through the sequence of activities for a typical order, the customer places an order. The order is sent to Kafka to a new orders topic. Step two is start the new order workflow. The Kafka consumer that's consuming off that new orders topic gets the order, and it starts a new order workflow in Cadence using the Cadence client. Step three, the order is ready for drone pickup. In an activity, we send the order ready message to the orders ready topic. Step four, in the drone workflow, in the activity, we send drone ready message to the drone ready topic, and the Kafka consumer gets an order ID and sends a signal back to the drone to start the order pickup. So this is the primary use case where we're actually using Kafka to do some coordination between the two different Cadence workflows. Step five is in the drone workflow. It's fly to order. It's an activity. Basically, it does all those computations to determine the next location for the drone flying from the base to the order location. And then finally, in that activity as well, it picks up the order from the shop. Step six is the drone workflow again, but it's flying to the delivery location, to the customer location, and that's an activity which does the computation for the movement flying towards the delivery location. And then step 6, finally, it drops the order, sends location updates to the order workflow every 10 seconds while it's in progress as well. This is so that the customer could potentially know an ETA and watch on their app, perhaps the flight path of the order being delivered to their location. Step 7 is in the drone workflow. Again, it's flying back to base. It's in an activity. It flies back to the base again. And when it gets back to the base, it recharges and starts the new drone workflow instance. Step 8 is back in the order workflow. This is the update location side of the story. It receives state and location signals from the drone workflow, updates the state, and finally it detects if it's been delivered successfully and then ends the order workflow. There's a lot going on there, but how many drones can we fly at once? Here are the cluster details for the experimental setup that I had in terms of the number of virtual CPUs per cluster type. On the client side, we had 8 CPUs. The Cadence servers had 6, and Cassandra had 18 servers. So there's a lot going on the Cassandra database side to handle all the persistence and event replaying. The load test we did, we managed to run 2,000 drones concurrently, which also meant, of course, that we had 2,000 orders concurrently, as is one order per drone workflow, which gives a total of 4,000 workflows. So here's a very simple visualization of the simulation running with only 20 drones flying. It's sped up quite a lot. I'll start it now because it does take a few seconds to proceed. All the drones start out at the base, which is the purple symbol there in the middle. The drones, you can see them flying around there at the moment, the black symbols. Orange symbols are the shops, and you'll see those pop up as the drone is flying to pick up the order. And once the order has been picked up, the orange symbol disappears, and then the drones head off to the delivery location, which is the red symbol. And when the delivery is successful, those delivery locations turn green, indicating a successful delivery. So there's quite a lot going on there. In a real system, you'd want to avoid collisions, and you'd also want to be able to do things like work out whether some of the shops are going to be particularly busy at certain times of day, so they can put on more staff and make sure that there's no congestion or delays around either the drone side of the story or the order preparation side of the story either. And that's what we're going to have a look at next. So the part 2 of the talk is about Kafka and machine learning using TensorFlow over spatiotemporal drifting streaming data. So the goal is to predict which shops will be busy in advance or not busy in this case. So shops are either going to be in 2 states, not busy or busy. And why was I interested in this problem? Well, it turns out that real-time machine learning is pretty common these days. It's more or less everywhere. For example, TikTok and cat videos. TikTok uses real-time machine learning and Kafka to make sure people are given the right content that they are more likely to watch to keep them engaged in the platform. There are some challenges around incremental machine learning in particular. It's a big data problem. There's lots of data for a start. It's fast data. There's streaming data. It's constantly arriving. You can't sort of put a hold on new data coming in. It's going to be coming at you all the time. And sometimes the data changes. So this is the problem of concept drift. You can't know in advance whether the concept will change over time, and it often does in the real world. So you have to be prepared for that and have some mechanism in place to adjust your learning to cope with that so that the learnt models are up to date and accurate. It's just-in-time learning, it's continuous learning, and the model must be up to date as much as possible at all times. Finally, streaming data is infinite, so you can't assume access to all of the past data. So you may only be learning over a subset of the data, probably only the most recent data. So let's have a look at how this works with the drone system that I've described. What is the drone learning problem? Well, the drone delivery system generates massive amounts of spatio-temporal data. The drone order data is sent to Kafka. Can we learn how to predict which shops will be busy an hour in advance of when they are or are not busy? This could potentially give the shop owners enough time to make sure they're ready to cope with the rush each time. Here's the architecture of the machine learning system. Essentially, I've just bolted Kafka and TensorFlow onto the order workflow part of the drone delivery system. The order workflow essentially produces a message every time an order is successfully delivered. I then aggregate the hourly data and determine the category busy or not busy. And this categorization is sent to TensorFlow via Kafka and Kafka streams. C is for cat. A long time ago, they came up with the Mark I perceptron in the 1960s. And TensorFlow is actually a descendant of that neural network model. It's a modern neural network framework which supports incremental learning, sort of baked into the way that it does the learning. So for the rest of the talk, I'll basically recount some of the experiments I conducted trying to successfully do incremental machine learning. So I tried doing this incrementally. I didn't try and solve all the problems at once. I didn't really understand what some of the challenges were and how well TensorFlow in conjunction with Kafka would work. So I tried doing solving the problem incrementally. So the first experiment was really just using still batch data only. There was no concept drift involved at all, and I didn't even use Kafka at this point in time. There were 6,000 samples used over a week's worth of drone deliveries. The class that I wanted to learn was whether the shop was busy or not busy in a given hour. Now, the class and other features are computed from hourly aggregated delivery and shop data. Other features included things like the day of the week, the shop type, the average delivery time, and more as well. Time was quantized into hours, location to suburbs. So there was a bit of cheating in a sense going on at this point. The features were predetermined for time and space. And the actual rule which was used to determine if a shop was busy or not was a combination of the shop type, location, weekday, and the hour of the day. Here are the TensorFlow training steps. Starting at the bottom with step 1, there's a whole bunch of steps that you have to carry out in order to train the model on data. Basically, you set up Python TensorFlow on the machine, you import pandas and numpys, define data columns and the class label, read the data into a panda data frame, split the data into training evaluation subsets, create a model which involves designing, building, and compiling a model. In this step, we use the Atom optimizer, which is just a common default optimizer that's used in TensorFlow. Step 7, prepare the training data into features and classes. Step 8, train and fit the model using order epochs. Step 9, evaluate the model. And 10, use the model on new data, assuming that it all works correctly. Evaluation is quite important with machine learning. You want to know whether the model is performing well or poorly and according to different metrics. So what matters? Well, accuracy is a common evaluation metric that's used, but it can be misleading unless you have roughly equal positive and negative samples. So another thing I did to simplify the problem a bit was to make sure I had a 50-50 split of busy and not busy shops. What else matters? Well, a confusion matrix is a common tool to determine the quality of model learning. Basically, you want to maximize true positives and true negatives and minimize false positives and false negatives. And it depends a bit on the domain whether that matters or not. But I made that one of the goals for this example. So what were the initial results? Well, I had 1 week of drone delivery data with shop busy, not busy, in a 50-50 ratio, as I mentioned before. Training, the accuracy improved during the training from 0.5, which is just guessing, to 0.88 over 125 epochs. The evaluation confusion matrix gave good results. As you can see, the majority of the outcomes were in true positives or true negatives. There weren't many false positives or false negatives. However, it turned out that there were a few problems. The results were not particularly repeatable. The accuracy was between 0.5 and 0.9 when I repeated the experiments multiple times. And interestingly enough, the training time also varied between 5 and 92 seconds. It was also sensitive to batch size. The number of samples used per epoch between 8 and 64, 32 seemed to give the most consistent result. And sometimes it gets stuck in a bad local minima, which is a tricky problem to solve because the optimization doesn't know that there's a better minima nearby. It just thinks, oh, I found the answer and I'll stop. So there were a few things I noticed. So that resulted in an experiment number 2. This was incremental learning, again, with no Kafka and no drift. The goals were continuous model training from the streaming data, using incremental learning, keeping the model up to date all the time, and useful for real-time use cases. And in theory, it can cope well with concept drift in the data. So this experiment had the same data as the last time, but I was using incremental learning. So the approach I used initially was to slice the data to get 100 samples at a time. This is essentially simulating what would happen in the Kafka case with the Kafka poll. I then fit the model with each sample, and I had a fixed number of batches, 8 and 20 fixed epochs. And then I evaluated against all the previous data. So here are the results. I use this type of graph to explain the results for the following experiments. Basically, time is the x-axis. So as the model continues to learn over time, it progresses towards the right of the graph. The accuracy is on the y-axis between 0 and the result of 1.0, 0.5 is just guessing. So what do you notice? Well, first of all, the accuracy does improve with time eventually. It took a while before the accuracy actually started picking up, but it did start improving eventually. The accuracy got up to about 0.8, which was comparable with the previous results with batch learning. But there is something slightly funny going on here. There's some oscillation going on. You'll notice that the accuracy goes up and then it drops significantly. It goes up again, drops. So there's a sort of an oscillation going on here, which is a bit strange and probably undesirable as well. So experiment 3 was incremental learning, this time actually using Kafka. And the results for this experiment were better, I think, compared to the previous ones. There's not as much oscillation going on, but the accuracy was worse. So the best case accuracy was about 0.72 compared with 0.9 for the batch learning on the same data. So yes, obviously there's a bit of a compromise here between batch learning with all the data and incremental learning, which can cope perhaps better with changes, but doesn't produce an absolute better result. So experiment 4, this is incremental learning again with Kafka, but this time I actually introduced the concept drift, which was the real challenge that I was trying to solve. So what happened was we introduced concept drift at the start of week 2. So we learned over 2 weeks of data. The first week had one set of rules applied consistently over the whole week. But then I changed the rules so that at the start of the second week, there was a whole new set of rules in place for which shops were busy and not busy. So this essentially would come as a surprise to the model. As you can see, the model accuracy did improve over the first week of learning and reached a maximum accuracy of 0.7 during that week. And when the concept drift was introduced at the start of week 2, the accuracy instantly drops to below guessing. So it's actually a lot worse than guessing at this point. drops to about 0.3. And again, the accuracy improves over the second week to 0.75. We still have the oscillation problem. So the accuracy is going up and down for some reason over the period of time. So I did a few variations on experiment 4. This is experiment 4B, where I reset the model. So reset the model after the drift. If the accuracy drops too much, then the idea is to reset the model and then retrain the model using only new data. This removes the pre-drift model inertia. And as you can see here, the blue line shows learning using the same model over the 2 weeks. The orange line shows what happens when we reset the model at the start of week 2 and we notice the accuracy drop significantly. This seems to help immediately. The accuracy shoots up to 0.9, but there is still oscillation and the accuracy drops to 0.7 by the end of week 2. Why are we getting oscillation? I thought it was time to actually try and understand the cause and maybe cure for the oscillation. But it turned out that we had accidental drift all along, basically. So even though the rules themselves weren't changing, the data was changing over time. Why was this? Well, because temporal features, that is day of week and time of day, were used to determine if the shops were busy and not busy. So we've got something in the actual data and in the concept, which essentially is time-based. And also I noticed some hours had no busy shops. For example, at the end of the day, the rules more or less meant that there were no busy shops for an hour or more. So the accuracy actually increased accidentally at that point as well. So there's a bit of a time bias and fixation going on here. Incremental learning may result in a temporal bias due to fixation on recent samples. This is apparently a well-known problem. Model overfitting, which is often indicated by oscillation on time series data, is a well-known problem. So if you have time series data and incremental learning, you end up going down a sort of a rabbit hole, which is somewhat strange and hard to understand. Can we fix it? Maybe. So one thing I tried was to actually just get rid of time out of the rules being used to determine if the shops were being busy or not busy. So this isn't really a fix because I was still trying to learn over rules that would normally include time, but I wanted to just double check and confirm my suspicion that it was the time features that were causing the oscillation. So this was experiment 4C. We removed time from the busy, not busy rules, and guess what? There was no wild oscillation anymore. With the reset model, there was a big drop in accuracy initially, but slightly better accuracy is achieved by the end of week 2. So in production, you could continue using the old model until the new one is trained up again. So just some quick conclusions to sum up. Incremental learning is fast. It should be able to keep up with streaming data in a production system. And incremental learning is able to keep the model up to date, more or less, in conjunction with resetting the model. Model accuracy may oscillate due to the presence of time features, fixation on recent data, changes in sample class distribution over time, and concept drift. Overfitting on time series data is something to watch out for and take action to prevent, mitigate. And maybe use multiple competing models concurrently is a good workaround. So spatial temporal bias in learning is probably going to be inevitable. The world actually is against you at this point. You only are at a single point in time and space when you are doing learning. You have access to past events in theory. You can't be everywhere at once in the present, and you don't really have access to future events. So unfortunately, this is the nature of physics, and reality means this is actually a challenging problem, but we've got some tools here at least that may make this a bit easier. Combining Cadence with Kafka and then TensorFlow to do the machine learning over real time. There are some challenges, but I think in the future, systems like this will be really useful to be able to produce models that are up to date and can cope with streaming data. So that's all from me. Again, thanks to the organizers for the invitation. I hope you enjoy the rest of the conference. And if you'd like to contact me, LinkedIn is probably the best one. And here are a few details of the Instacluster website as well. So I hope you enjoyed the talk. Thank you very much. I'll hand back over to the organisers now. Thank you.
The API Connect Hong Kong 2023 conference is powered by bNovelty Limited. Check out more API-related education content on bnovelty.com or apidays.hk for more information.